Let's start. I think for today's lesson, we will go through some simple stuff. I would say basic stuff as well. Now, you may want to take out your notebook and jot down the important things along the way. Now, this is for chemistry, so we'll go through some basic units. Now, admittedly, I would say the units for chemistry are not as expensive as those for physics. So I will go through those those units strictly pertaining to chemistry. So note that there will be more units in under physics. Now let's take a look. Well, starting with mass. Well, no doubt you should realize that the SI unit for mass will be kg, but I'll be very upfront to say that in chemistry, we use tons quite often, tons and grams quite often as well. Okay, maybe not tons as such, but grams are definitely used very, very often. In fact, in chemistry, grams is used more often than kg. So just keep that in mind. And of course, you're expected to know the conversion among these three units. Now, a very simple, I would say, revision. Make sure you realize that 1 kg is equivalent to 1000 grams. So when you convert from kg to grams, you simply multiply by 1000. And of course, if you want to convert from grams to kg, you divide by 1000. Now, tons is used especially when you are talking about large-scale production of chemical substances, plant size considerations. You are not going to fit just a few grams or a few kilograms into the chemical plant. You are typically feeding tons, many tons, hundreds of tons even, and you're producing again tons of products. So therefore, it makes sense for you to know that 1 ton is equivalent to 1000 kg. Well, of course, from ton to kg, you multiply by 1000. And if you decide to reverse the relationship from kg to tons, you divide by 1000. So yes, you will definitely encounter mass in chemistry, and these are the three units you're going to see. Nothing more than that. Now, of course, to measure this mass, we are looking at the chemical laboratory. All right. Now, let's try to keep our scope narrow. So basically for chemistry, in fact, not just for these measurements, but also for reactions, reaction conditions, we are restricting ourselves to the chemical laboratory. That means, can you do this in the chemical laboratory? Do you do other things? Or do you just use this particular piece of equipment available in the lab? So most of the time, maybe not all the time, as I said, sometimes chemistry also deals with large-scale production in the plants, but most of the time, our scope is within the chemical lab, right? So of course, in the chemical lab, you have your weighing balance. Now, if you are very observant, you notice that it typically goes down to 2 decimal places for the um, hand balance. Units will be in grams. And for the analytical balance, they are a lot more accurate and they typically go down to 4 decimal places in grams. So just keep that in mind. This is for the general pen balance. And this is for the more accurate analytical balance. Now, of course, if you go to industry in a chemical plant, you have larger balances and they typically weigh kg and possibly they weigh in terms of tons as well. But for, I would say for secondary school chemistry, we hardly mention about those kind of devices. Let's go on. Time is another important factor in chemistry. Now, well, of course, you're supposed to know the 3 basic units: second, minutes, and hours. So I do not think I need to elaborate. All right, so make sure you realize that 1 minute is 60 seconds. 1 hour, of course, is 60 minutes. But you should be able to convert from hour to seconds as well. So basically 1 hour is 3,600 seconds. Now, obviously, you are expected to be able to convert backwards from seconds to minutes, and of course, from seconds to hours. Very occasionally, you may encounter days. And the short form is D. This is not so common. So once in a while, you may see this days in chemistry. Now, obviously, you are expected to know 1 day is 24 hours. And of course, I don't think I want to work out the rest, how many minutes or how many seconds, but you should be able to do that. So you should be able to figure out how many minutes this is. And of course, how many seconds 1 day has. Now, as I said, for chemistry, in the lab, the common piece of apparatus that we use to measure time will be the stopwatch. Now, you are expected to know this. Like, let me just repeat, make sure you understand balance, stopwatch, because you are expected to provide this in your answers when they ask what sort of apparatus do you need to run this experiment. So make sure that these are the common pieces of apparatus available in the chemical lab. Now, the next parameter or the next quantity will be volume. Again, for chemistry, there are 3 common units for volume. Yes, no doubt. You must realize that the SI unit will be cubic meter. But not surprisingly, cubic meter is a very large volume, at least in the laboratory. Therefore, you are more likely to see cubic centimeters or decimeter cube. Now, again, guys, you have to be able to interconvert between the 3 different volumetric units. Now, just to be sure, cubic centimeters is equivalent to ml. Now, of course, if you have been looking at packaging, like on your foodstuffs or on the bottle of shampoo, bottle of oil that you bought, units that are often used to be in ml. However, for secondary school, they stick to cm cube, em cube, and meter cube rather than ml and liters. But nevertheless, just to help you relate to the real world, 1 cm cube is equivalent to 1 ml. Now, what else? Now, this one dm cube you may not have used previously, but I can assure you that this is definitely coming up. This is definitely used for upper set chemistry. Now, before I go to dm cube, let's look at one dm. What is dm? Well, dm stands for decimeter. And even though this will not be asked in chemistry, it helps you to understand how dm cube comes about. Now, essentially, 1 dm is 0.1 meter. And therefore, 1 dm is okay. Hold on, let me just rewrite this. Right, let me rewrite this. 1 dm is basically 10 cm. And it is, as I've written earlier, this is equivalent to 0.1 meter. So there is such a unit as dm, decimeter. Now, again, not surprisingly, decimeter is a unit for length. No, but for chemistry, we don't talk about length that much. We talk about volume. Okay, so as you talk about 1 dm cube, you are essentially taking 10 cm and cubing it. That would, of course, give you 1000 cm cube. Now, if you're familiar with the units of liter, this is equivalent to 1 liter. All right, but as I said, for upper sec nowadays, we do not use liters and milliliters. All right, instead they stick to cm cube, dm cube, meter cube, cm, and so on. Now, what else? I can also write further. Now, remember, 1 dm is 0.1 meter. So 1 dm cube is 0.1 meter, and cubing the whole quantity as well as the whole value and the units. So that would be 0.001 cubic meter. Now, lastly, cubic meter is, again, as I said, a very large volume. It's not encountered in the lab that much. More likely you find this unit being used in the industry, but of course, you will also find this unit being used more often for gases. Now, gases encompass a large volume. All right. And of course, gases are very low in density. So therefore, even though you may have a large volume, the mass is not that much in comparison to liquids. So just be very mindful, cubic meter is often used for gases. Now, what you need to know, and probably you already have seen it here, Right, 1 cubic meter is equivalent to 1,000 cubic, 1,000 dm cube. If you go for the 1 cubic meter, is equivalent to 1 million cm cube. So if I do a quick summary, so 1 cubic meter or if I want to convert cubic meter to dm cube, I simply multiply by 1,000. And if I want to convert dm cube to cm cube, okay, likewise, I multiply by 1,000. Well, obviously, if I want to go from cubic meter to cubic centimeters, I multiply by 1 million. Now, of course, the reverse is true. From cm cube to dm cube, I divide by 1,000. dm cube to meter cube, I divide by 1,000. And from cm cube all the way to cubic meter, I divide by 1 million. Be familiar with all these conversions because you will see all 3 units being used in chemistry. Now, next, how do we actually measure volume? Now, again, let's restrict ourselves to the chemical laboratory. Now, in terms of liquids, okay, there are two broad categories of apparatus regarding volume. You measure the volume of a liquid or you measure the volume of a gas. All right, so be very clear what kind of states of matter you're measuring. Now, if it's a liquid, I hope this is nothing new to you. You use a beaker, measuring cylinder, pipette, or burette. So these are the 4, I would say, standard apparatus for measuring liquid volume. Now, of course, liquid is, I mean, in a beaker, basically that only gives you an estimated volume. Beakers are marked. Yes, they do have markings on the wall, but essentially I will not trust these markings. Simple reason, because the mouth of a beaker is rather wide. So first thing first, you are going to have a hard time looking at the meniscus. It is going to be very, very wide. Okay, so it's hard to actually find the exact level of the meniscus. So to make a long story short, these markings only give you an estimated volume. Now, measuring cylinder will be something like this. And typically, the mouth will be a lot narrower. And the markings here will be, I would say, more accurate. And based on your syllabus, the accuracy is down to cm cube. Now, just one question. How much can a measuring cylinder measure? Well, I think it all depends. I mean, since you guys are not here today in the classroom, I can't exactly show you that easily. But obviously, there are very small ones. Perhaps this one can only measure up to 10 cm cube. But of course, there are also really large ones. And in fact, they are so large that the mouth of the membrane cylinder is actually comparable to the mouth of the beaker. Now, something like this, I can tell you the largest I've seen is for 5 dm cube. Right, so quick reminder, 5 dm cube is equivalent to 5 liters, so it is really huge. But in general, for your syllabus, you take it that the accuracy is down to cm cube. Now, pipette is this thingy, and yes, you need to be able to recognize it because you have a practical exam. And of course, in the exam, instructions will tell you use a pipette to measure, let's say, 10 cubic centimeters of a liquid. Now, it makes sense that you select the right apparatus according to the instructions. Now, for your syllabus, a pipette has a line down here. So if you suck your liquid upwards, and the meniscus reaches this line, you would have pipetted, let's say, 10 cm cube. Right, so it goes without saying, there are many different sizes for pipette. There are many sizes. The smallest I've seen would be 1 cm cube. All right, it is, again, it'd be good if you're here in the classroom so they can show you it's just a very narrow tube. But there are also large ones, very large pipettes that goes up to 100 cm cube. So this would be the typical sizes, and you have other sizes in between, maybe 2 cm cube, even 3 cm cube, 5 definitely, 10, 20, 50, and so on. And the last piece of apparatus that you need to know will be the burettes. So this is the burette. It's almost a straight tube, except at this point there is a valve. Alright, so what you do is, before I go on, there are markings here also. Now the markings actually stretch all the way along the wall of your burette. Now, in the lab, there are 2 typical sizes. Alright, either the more common one will be the 25 cm cube. So the maximum volume is only 25 cm cube. There's a larger version, which is 50 cm cube. This is not so commonly seen, but still available. Right, so take note, your volume doesn't extend forever. It doesn't go up to 1 liter or 1 dm cube. Right, so these are the only 2 typical capacities. So how it works is this. When I use a burette, okay, so what I do is I'm going to fill this up. But not exactly to the mark, but I fill this up higher than the mark. And next, I open this valve. Now this valve is there is a position for open, fully open, and a position for fully closed. All right, so of course, initially it is closed, but I open it. And of course, your liquid will flow downwards. Now, your liquid will flow downwards until it reaches this mark here. Now, if you look carefully, this mark is 0. And once it reaches this mark, I mean the liquid has reached this mark, I close the valve. Okay, so now my liquid is exactly at the 0 mark. Now, this burette allows you to release an exact amount of liquid. How accurate? Down to 0.1 cm cube. So let's imagine my mark here is 10. Let's say this is the 10. This is the 10 cm cube mark. Okay, so what I do is, once I have prepared the burettes in this manner, I move it over a conical flask or maybe a beaker. Then I open the valve. And of course, your liquid will start to fill. Will flow downwards into the not volumetric flask, but the conical flask. Now again, you allow your liquid to flow downwards until this 10 ml mark. Right. So essentially, it means that this volume or 10 cm cube has flowed into the conical flask. Right, so yeah, that's the very simple theory of how it works. The other piece of apparatus that you sometimes get to see in the lab is what they call a gas syringe. Now, this one is strictly for measuring gases. If you ever need to measure a gas, volume of a gas, there's no need to think further, just use a gas syringe. There are other methods that you sometimes see in upper sec, but I don't think I want to mention them to you now because they are not commonly seen until we come across questions that involve those apparatus. Okay, otherwise, volume of gas is measured by gas syringe. Now, it looks something like this, as the name implies. Yeah, of course, it's a syringe. It looks something like this. I have a tube here, a glass tube. And you have the gas moving from left to right. All right, so what I do is I simply feed my gas syringe over here. Now, obviously, there are many different versions, but this is just one of the possible versions that you see. And there's a plunger here. Okay, so there's a plunger. Now it's movable. Okay, so this is your movable plunger. Now, of course, there are markings here as well. okay, along the wall of the syringe. So as your gas goes into here, your plunger will move from left to right in this example. And of course, this marking here will tell you the volume of a gas collected. So gas syringe is used to measure volume of a gas. Perhaps the last, I would say, parameter that you need to use in chemistry will be temperature. So you notice we don't really have that many parameters for measurement: mass, time, volume, and temperature. Now for temperature, well, of course, the units that we use will be degrees Celsius in chemistry. Now, obviously, perhaps not so obviously, you may come across the SI unit. Now take note. For temperature, SI unit is actually Kelvin. Okay, but I believe I've never seen Kelvin being used in chemistry before. So the unit you're likely to see will be degrees Celsius. Now, of course, basic stuff or primary school stuff like 100 degrees Celsius, 0 degrees Celsius, these are important benchmarks. So 100 will be your boiling point of water, and 0 will be your melting point of ice. Well, how do we measure temperature? I think there's nothing new. You definitely know about a thermometer. But it's also quite common to be using a temperature sensor or a temperature probe. And again, it could be linked to a data logger to record the change in temperature with time. I don't think there's much I want to elaborate about this. Just keep these two operators in mind. Now, a few other things. All right, I think that would cover the parts on the measurements for chemistry. Let me just make a pause here.
I was talking to I know with the settings and stuff that you want to look at some.
No, apparently I can't pause, but let me just grab a drink first.
Sorry, direction. No. I think my questions are any questions. But still, I don't know if divide. Is there a way I can divide? If I should divide the time, it's probably start with. This one is the blue line. But if I change the sign, I do the fraction. Oh yeah, I remember. This baby. This one. On the 8 to the power something I don't see more than 180 one times. I see more than 180 one times in input times. Right? I need to write it. Okay. But it doesn't go wide, that's right here. Same thing now. In this two minutes ago. then multiply something like 6H squared is a fraction, does it go to the numerator or something like that? That's a fraction. Okay. Yeah, also making some things, but okay. 0 1 at least already right now. Right. Yes, no, it's depends where it's as it is, I think go to the return, but it go to the so I think oh, multiply it.
Now let's continue.
Only that's 5. Not actually, right? No,
There are a few guesses that you want to be aware of. Yes, just now we mentioned about collection of gases or measurement of gaseous volume. But what gases are we interested in? Well, these are the specific ones. Okay, O2, H2, CO2, N2. Now, I want you to remember these four gases especially, they are odorless and colorless. You can't smell them, you can't see them. But I want you to be very clear. This is, of course, in air. O2 is inside air, N2 is in air as well. And I want you to remember this is the percentage of N2 in air, and this is the percentage of O2 in air. You have to remember these two numbers, 78 for N2, 21 for O2. Now, be very clear, and H2 is hydrogen. This is not in air. What else do you need to know about hydrogen? Now, personally, I would be very careful with hydrogen. It is highly explosive. And perhaps I mentioned this before, if you ever see a hydrogen tank, H2 tank, gas tank for hydrogen, it is bright red. And I believe that helps to remind you how dangerous H2 is. Okay, it's painted bright red. Now, of course, you do not need to know the color of the gas cylinder. But again, just for info, for O2, what do you think the color is for O2's gas cylinder? Now, this is typically painted black. So there's still an element of, I would say, danger there. I mean, we tend to take note of stuff that are black. Well, at least for me. Right, but again, O2 is dangerous, yes, but definitely nowhere as dangerous as H2. Now, N2, what do you think the color is? Now, N2 is inert. Perhaps you want to write down, even though this may not be asked all the time, it's an inert gas. No, it doesn't really react that much with other substances. So that is, well, good news and bad news. The good news is it is pretty safe. It's generally safe. Okay, the bad news is, of course, you can't use it for your reactions. You can't use it much for to make other products. Now back to the color, you would expect this to be gray. All right, so I mean, gray is a pretty, I would say, a mild color. Usually it tells you that there's not much need to take note of it. But again, it's not part of the syllabus to remember the colors. However, the other things are part of the syllabus, like an inert gas, Explosive, yes, this one. Please remember that. And of course, in real life, you will learn to respect hydrogen gas. It's highly dangerous. Perhaps you'll come across this test for H2. All right, so you put a lighter spin at the mouth of a test tube, and if high H2 is given off, basically you will hear or you will observe a tiny explosion in the form of a pop sound. So more about this further down the road, but well, this is something that you may get to do in your practical. Let's go back to O2. Now, O2, I didn't write it down, but I assume you already know it's important for respiration. I mean, basically, it's important for survival. All right. Animals, plants, they need O2, but I don't think that you need to know that, at least not for chemistry. But you need to know this. O2 is needed for combustion. All right. Combustion means burning. So when you want to burn something, oil, petrol, diesel, even burning of metals, you need O2. Well, there's a test for O2 as well. I mean, this is based on the secondary school syllabus. All right, put a glowing spleen at the mouth of a test tube, and the glowing spleen rekindles or relights itself. Just to be sure, what's the difference? Glowing, you see this orange lights, orange glow, whereas rekindles means you see it bursting into a flame. All right, you see a flame and it rekindles. And also, just compare with lighted versus glowing. So lighted means a flame is present. Okay, you really see it burning. Whereas orange is, well, it's on the verge of being extinguished. Now, lastly, don't forget CO2. Now, CO2, I didn't put it here, but it's inside air as well that you ought to know. Even though they don't, most of the time, they don't ask you about the percentage in air. So it's about 0.03% in air. Now, of course, CO2 is part of your respiration. It's also involved in photosynthesis, but I won't go into that, at least not for chemistry. So how do you test for CO2? Again, you should have seen this before since primary school. Basically, you bubble an unknown gas into lime water, and of course, you get a cloudiness. Now, I think for upper sec, they probably do not like to use the word cloudiness or murkiness. Instead, they want you to write a white precipitate forms. Okay, and of course, please start getting used to seeing this word precipitate. Precipitate means a solid. All right, that appears. Typically, that appears from a clear solution.
Realize your multi-type refraction by
Now, the other misconception that some students have is lime water. Again, it can be quite embarrassing when you compare lime water with lime juice. They are totally different. Don't ask me why they want to use the word lime. I maybe tell you one of these days, but not now. So anyway, lime water is essentially calcium hydroxide solution. And if you have encountered chemical formulas in your lower side, This is the formula for calcium hydroxide, and it's in aqueous form. So that is lime water. Try to remember that. You will see it over and over again. Now, in addition to the four odorless and colorless gases, we have a few pungent gases. Now, typically pungent means it doesn't smell nice. It's foul smelling. Like this ammonia. Well, ammonia is, well, present in urine. So not surprisingly, ammonia gas smells like urine. Now, of course, as a note, my formulas are written without the subscript because of the way this platform is formatted. Make sure you write it in this manner. Likewise, this is sulfur dioxide. Make sure you write it in this manner with the subscript 2. Cl2 is chlorine. Okay, this is HCl. Hydrogen chloride. Okay, what else do I need to tell you? Now, all these are pungent gases, and the good news is, I mean, the bad news is they do not smell nice, but the good news is, okay, let me just share with you the second piece of bad news. Well, they are all essentially toxic to you, but the good news is you can smell them. You know that they are there. And of course, that also motivates you to get away from them, right? So these are all toxic. Now, obviously, there are gases which are toxic and odorless. Those are the dangerous ones. We'll touch on one of them later on, like carbon monoxide, but here we'll restrict ourselves to this few. Okay, anyway, chlorine gas, it smells like, well, swimming pool. Yeah, because they use the same compound or the same substance in to disinfect swimming pool water. So by itself, chlorine gas is yellowish green. The rest are all colorless. Okay, so this is ammonia is colorless, SO2 is colorless, HCl is colorless. But I also want to qualify that they're only colorless when they are pure. And some of them can react with substances in the air and they form something else. Okay, I won't go into that part though. However, the thing you need to know is these pungent gases tend to react with water. Okay, so keep that in mind. This is an important fact. Once they can react with water, you cannot collect them by running them through water, as you should see later on. So there's another experiment technique that you may want to be mindful of. Now, here we are talking about collection of gases. Be very mindful. This is different from measuring the volume of a gas. Right. But of course, let's be also very clear about this. When we measure the volume of a gas, we are actually using a gas syringe. And as I said, it looks like this. you are actually using the gas streams to collect the gas as well. So take note, if you need to measure the volume of a gas, you are actually collecting the gas too at the same time. But there are instances in which you only want to collect the gas. You're not so, I mean, of course, you need to know roughly what's the volume, but you're not so interested in the exact volume. So, in other words, for strictly collection of gases, you only want a different set of operators. You do not need a gas syringe to do that, even though you can use a gas syringe. Now, before we look at the methods, you have to first understand what gas you are collecting. Now, if your gas is insoluble in water or there's no reaction in water, now this is an important thing or important parameter to be aware of. So essentially, you're referring to your odorless gases. 1, 2, 3, 4. These gases do not react with water. Okay, so you can collect them by this method called displacement of water. It looks something like this. I have a tube that goes downwards and it hooks upwards again. So this is your gas. And you have a basing here. Here you have this apparatus here, a glass container. And typically this apparatus is filled with water. All right, so what happens next? Your gas will bubble. And it starts to fill up this headspace here in the glass container. All right, so this is your collection chamber. All right, so you allowed it to pass through water and gets collected right here. All right, so this displacement of water. Now, as I said, this is water. So your gas is allowed to bubble through upwards through the water before it gets collected in this chamber. Now, there are two other methods. All right, one is displacement of, the other two methods are based on displacement of air. And under displacement of air, there are two possibilities. Now, essentially, when do we use displacement of air? When that gas is insoluble in water or it has no reaction with water. Oh, let me rephrase it. You use the displacement of air as a method to collect a gas when the gas is soluble in water or can react with water. So again, two possibilities, and you have to decide on either one. All right, you cannot use, it depends on the gas as well. So what is outward delivery? All right, it is simple. You simply allow your gas to go upwards into this container, glass container here. Okay, so this outward delivery. And of course, the important thing is Okay, the important thing is your gas has to be less dense than air in order to float up to the top here. But how do you know whether a gas is less dense than air or not? Now, there's a simple way, which I'm just telling you right now, even though this topic will be covered later on. Now, one example of a gas less dense than air is this ammonia. Now, if I try to calculate the molecular mass of ammonia, right? Basically, you sum up the atomic masses. Look at your periodic table. Nitrogen is 14. I have 3 hydrogen atoms. And if you check the periodic table again, the atomic mass of hydrogen is 1. So altogether, you get 17. So this is the molecular mass of ammonia. But what about air? Now, I won't go through how to derive this figure, but it helps if you remember air has a molecular mass of about 29. Okay, so I'll put the symbol as MR. So as long as your gas has a lower number than 29, it is less dense than air. This guideline works most of the time, almost all the time. But one question you may ask, can I use this method for other gases, like hydrogen? Well, hydrogen is not soluble or doesn't have a reaction with water. Answer is yes. Right, so for hydrogen, I can use displacement of water, as shown here, or I can use upward delivery. Now look at hydrogen. This is H2. Can you try calculating the molecular mass? Yeah, it's made out of 2 hydrogen atoms. Each atom is of atomic mass 1, so it's only 2. Now, by the way, just for info, this is the lightest gas or least dense gas. Okay, in the world, of course. Now, lastly, the other method is downward delivery. Now, both upward and downward delivery are considered a displacement of air. And you can probably figure out how it's like. So again, I have a downward tube, glass tube usually, so your gas goes through the tube. And you typically just put a glass container here. So in this case, you allow your gas to sink to the bottom. Okay, you allow your gas to simply sink and accumulate at the bottom of the container. So that is downward delivery. Not surprisingly, this is reserved for gases which are denser than air. And this will be, not just denser than air, but they are not supposed to react with water. Meaning you can't use displacement of water, so therefore you have to use downward delivery. So I leave it up to you to try calculating the 3 molecular masses of these 3 gases. yeah, try to convince yourself. Make sure your values are more than 29. Remember, 29 is for air. Alright, so yes, they are heavier, they are denser than air, so they will sink to the bottom and gets collected here. Okay, I believe now will be a good time to make a stop. So of course, if you have questions, feel free to send a message to me. Right, well, I prefer your questions to be sent via Telegram. Okay, so I'll make a stop at this point.